Hey, welcome to The Explainer. Today we're diving into something that's really at the heart of modern physics. How do we actually describe reality for things that are moving? It's a journey into the very fabric of space-time itself. And what's really cool is we're going to see there's more than one way to draw that map.
Okay, so let's get right into it. The road we're taking today comes straight from chapter 13 of a book called Newton and Relativity. And what makes this approach so awesome is the foundation it's built on. See, the formulas it uses were all worked out from classical principles without ever needing to assume that the speed of light is constant. It just goes to show you there's more than one way to figure out how the universe works.
So here's the fundamental problem we're trying to solve. Imagine you see something happen at a specific place and a specific time. Now, I see that exact same event, but I'm flying past you at an incredible speed. How do our measurements line up? How do we translate the coordinates of that event from your point of view to mine?
All right, so let's start with the classic, the one most of us learn in school. This is path 1, the famous solution that Albert Einstein came up with back in 1905. Einstein built his entire theory on 3 really powerful pillars. First, the principle of relativity. Basically, the laws of physics are the same for everybody. Second, linearity. The math has to be consistent, no weird jumps. But the third one, now that was the real bombshell. The idea that the speed of light, c, is a universal constant. It's the same for every single person, no matter how fast you're moving. Just think about that for a second.
And this is where the magic really happens. When you force your math to obey that strange new rule about light, this special term just naturally pops out of the equations. It's called the gamma factor. You can think of it like a correction factor that only becomes important at really, really high speeds. And this little guy? It's the mathematical engine behind all the wild effects of relativity, like time slowing down and distances shrinking.
Look, this method is absolutely brilliant, but it does force you to accept a super weird idea about light right from the get-go. So you have to wonder, what if we didn't? What if we tried to build the same theory but from a more, physical, intuitive starting point? And that brings us to our second path, the alternative. We're about to try something pretty radical. We're going to derive the exact same rules for space-time, but this time, we're not even going to mention the speed of light.
So our new starting point is an actual physical thing that happens, length contraction. It's this idea that the faster something moves relative to you, the shorter it physically appears in its direction of motion. And the book shows how this can be figured out from other classical ideas. So instead of starting with an abstract rule about light, we're starting with a tangible, measurable consequence of motion.
Okay, here's our setup. We've got an observer just chilling out, we'll call him O, and we've got a moving observer, O prime. Now here is the absolute key to this whole approach. We are not going to assume that time is universal. We're leaving the door open to the possibility that their clocks might just tick at different rates.
First, let's just get our bearings. At the slow, everyday speeds we're all used to, the math is super simple. A moving object's position is just where it started, plus its speed times time. And notice, time is exactly the same for both people. T equals T prime. This is the world we think we live in, no surprises here.
But as soon as we crank up the speed close to the speed of light, things get strange. Our resting observer, O, actually sees the ruler in the moving frame as being physically shorter. This direct observation, based on our starting point of length contraction, gives us our very first relativistic equation for the space coordinate.
And here's where it gets really clever. Illustrating a core idea of relativity, this whole effect is perfectly symmetrical. From the moving observer's point of view, it's the resting frame that looks like it's squished. This observation gives us our second symmetrical equation for space.
And now for the big payoff. We have 2 different equations that describe space, just from 2 different viewpoints. So what happens if we set them equal to each other? Well, the space coordinates all cancel out in this really elegant way, and it lets us solve for the one thing we weren't even looking for, time itself. And there it is. Just look at that result. By starting only with the physical reality of length contraction, we have derived the exact same set of equations. These are the complete Lorentz transformations, the fundamental rules that tell us exactly how to translate measurements of space and time between any 2 moving perspectives. It's incredible.
So, what does this all mean? We've taken 2 completely different logical journeys, but we ended up at the exact same destination. What does that tell us about the universe?
Well, this comparison really shows the profound difference in the journey. Einstein's traditional method asks you to take a huge leap of faith about light right at the beginning. This alternative method, though, it builds a staircase for you, step by step, from things we already knew from classical physics. It only confronts you with the weirdness of time as the final, unavoidable conclusion.
And that right there is the core takeaway. In one journey, These transformations are the rule you have to accept to even start. But in this other journey, they are the logical destination you arrive at. That completely changes how you think about space and time not being absolute. One is an axiom, the other is a discovery.
Ultimately, what this proves is just how incredibly consistent the mathematics of our universe is. Whether you start from the top down with the strange rule about light, or you build from the bottom up from a physical effect by contraction, you uncover the same deep truth. Space-time isn't a fixed stage. It's this dynamic, flexible fabric, and there's more than one path to figuring out its secrets.
It really leaves you with a fascinating question, doesn't it? If there are at least two completely different logical paths to a concept as huge as relativity, what other bedrock principles of science are just sitting out there, waiting for someone to find a totally new path to them?